Yes, hi everyone. I'm current Irene, and this is Group 48. So our project is the plurimetric machine learning architecture for non-invasive anemia detection through conjunctival image analysis. So our project focuses on developing a non-invasive method for detecting an anemia using machine learning and conjunctival image analysis. Instead of relying on blood samples, we use images of the inner eyelid to estimate signs of low hemoglobin levels. Um, so slide 2 has the contents of the presentation. In this slide, I'll first explain the background of of our anemia project and why this problem is important. Then I will discuss related research and identify the gap that motivated our work. After that, I'll explain the problem statement, the methodology, the data description, the model architectures overview, the envelopes and deployment, then the limitations and conclusions, and the references. So the background and the introduction. Anemia occurs when the body has insufficient hemoglobin to transport enough oxygen in the blood. This condition can cause fatigue, weakness, dizziness, and in severe cases, it can become life-threatening. The condition affects millions of people globally, especially children and pregnant women in developing countries. Currently, diagnosis mainly depends on blood tests, which are accurate but invasive, sometimes expensive. However, doctors often observe conjunctival pallor as an early clinical indicator where hemoglobin levels are low. The inner eyelid becomes pale and instead of reddish. So our project, instead of using the blood test, we use the eyelid, which is kind of cheap, and you can easily get you can easily get the result if the person is anemic or non-anemic. So the related work, we have one from 2019, the other one from 2022, then two from 2025. So the problem statement, we have the domain application problem and the computation problem. For domain, anemia affects millions, especially in areas lacking medical labs. Current blood tests are invasive, expensive, and inaccessible. And then the computational problem, developing a reliable computer vision system to detect anemia is challenging due to variations in lighting, skin tone, and image quality. So the methodology, we have 4 steps. You extract the eye region, then you convert color space, you extract the features and train classical models. First, conjunctival images were collected and pre-processed. Pre-processing involved resizing images, removing noise, and standardizing color information. And then next, we have converting color space, where the color-based features were extracted because color intensity is strongly related to blood concentration and hemoglobin levels. Then after we have feature extraction, we trained several machine learning models to classify images into anemic and non-anemic categories. Finally, we evaluated model performance using metrics such as accuracy, sensitivity, specificity, and area under curve. Then the data description and exploratory data analysis. A data description. We use two countries. We have India and Italy. Where India we have 123 patients and India has 95 patients. Each image is associated with hemoglobin value, gender, and manual segmented conjunctival regions. The data set is intended for non-invasive anemia detection, image segmentation research, computer vision analysis of conjunctival pallor. The objective of this exploratory data analysis are to identify potential country-based based bias, then understand the demographic distribution, analyze hemoglobin distribution and anemia prevalence, then explore relationships between hemoglobin and age and gender, then investigate image color characteristics. The output results and discussions. So these graphs that we have, they show results using figures, tables, graphs with clear axis, legend, and scaling. So the first graph shows the age distribution, and its purpose is to understand the age spread. Then the second graph, it shows the age distribution by country, whereby its purpose is to compare populations. And then the third graph is about gender distribution, and each purpose is to check the balance. Then the third is gender distribution by country, whereby its purpose is to detect the imbalance. Then the age distribution by gender, whereby its purpose is to detect demographic differences. And then our next slide, it shows the results and discussions about the hemoglobin visualizations. We compared predictions across different samples and observed that clearly and well each images generally improved performance. So here the first graph shows the hemoglobin distribution, where it shows that the population with the highest hemoglobin, and then the other one shows the hemoglobin the hemoglobin versus age, and hemoglobin by country. Then the expected results, since the system relies on image capture, it can potentially be integrated into smartphones or portable devices, making screening services more available in remote communities. This slide, it shows some of the image samples that we extracted from the data sets we had. You can see these ones, they clearly show that the person is anemic because they do not have enough blood. Then this one, this histogram shows how the red, green, and blue pixel intensities are distributed across all the images, helping you see which colors are more common and how varied they are. Then our next, it shows the image brightness distribution. This plot shows how the overall brightness of the images is distributed, letting you see which brightness levels are most common and how spread out the values are. The model architecture overview. So these are the model architecture that we have. The first is the color histogram shallow neural network, where the first step we input the image, the conjunctival image, and it is split into three, which is the RGB histogram, the lab histogram, and the HSV histogram, where it is now concatenated into a 2-8 three-dimensional feature vector, which is fed into three layers: the input layer, the hidden layer, and the output layer. And then they give us one output they give us a final result to show if the person is anemic or non-anemic. And then the second is the depth-wise separable convolutional neural. Here we input the image, the eye sample, and then the data augmentation, where you rotate, you flip and increase the brightness to increase the number of the data sets. Then after that, you resize into one normal size, one standard size, and then after that, it is fed into four layers of the depth-wise to give they are fed into four layers of the depth-wise, then fed into the global average polling, then the dropout regularization, and then after they give us one output to show if the person is anemic or non-anemic. Then our next is simple color ratio classifier. Here we input our conjunctival image to give us the R mean, the G mean, the B mean, and the average mean, and then and then they're compared using the RG ratio. Here we use the mathematic values to get the values. We use the mathematic values to get the results, show if the person is anemic or non-anemic. And then the third, we have the gradient boosted color trees. So the model performance comparison and evaluation, we have our models to show the accuracy, the area under curve ROC, and the sensitivity. And our deployed model, the multi-architecture CNN, you can see it has the most accuracy and the AUC and the sensitivity. Also the accuracy. According to this, you see here our deployed model, the multi-architecture it has the highest accuracy. Also on this one, it is our deployed model that has the highest sensitivity and specificity. Then the model compression knowledge distillation. Uh, for model compression knowledge, To make the system suitable for lightweight devices, we explored model compression using knowledge distillation. In this approach, a large and powerful teacher model transfers knowledge to a smaller student model. The student model becomes faster and requires less computational power while maintaining acceptable accuracy. This is important for deployment on mobile or low resource healthcare systems. So these are the results from the model compression knowledge. The final results demonstrate that machine learning combined with color analysis can support non-invasive anemia screening. The envelopes and deployment. We considered envelopes practices to ensure the model can be maintained, updated, and monitored effectively. The deployment pipeline can include image upload, preprocessing, prediction generation, and result visualization. A web or mobile application could allow healthcare workers to capture conjunctival images and receive instant screening feedback. These are the limitations, the features, and the conclusion that we get from our project. At the current limitation, smartphone algorithm apply proprietary nonlinear while balancing that can override physiological color signals. Then our conclusion, we have non-invasive anemia screening from conjunctival images was demonstrated to be achievable through a photometrically disciplined colorimetric machine learning architecture. So these are some of our references that we got as we were doing our work. Yes, thank you very much.